And we're on lesson 6, and now that we're experts at graphing them, we're going to solve some problems with exponentials. Sorry. There are 5,000 yeast cells in a culture. The number of cells grows at a rate of 25% per day. So we're going to complete the chart. So you started at 5,000. So at the beginning of our story, we have 5,000. Now they're growing at an alarming rate. We're going to add 25%. So how do I figure this out? Well, I want to figure out what 25% of 5,000 is. So on my calculator, I'm going to do 25% of 5,000, which is 0.25 times 5,000 is 1,250. So the next day, I have another 1,250. So this is how many I have on day number 1. The day after that, I've increased by another 25%. So this time I'm doing 25% of 6,250. So if I do that, I get 1,562.5. I don't know if you can have half a yeast cell, so I'm going to assume not and round it up. But that's how many I increase by the next day. So I'm going to add that to my 6,250, and I'm going to have 7,813 now. They're going to take over the world. The day after that, I'm going to multiply 7,813 by 25% and grow again. Gets me 1,953.25, but I don't think you can have a quarter of a yeast cell. So I'm going to add this number to 7,813, and I now have 9,766 yeast cells in only a couple of days. I have almost doubled. So we want to create a model that I wouldn't have to be doing this table of values over and over again. So the number of yeast cells, I'm going to say A for amount, because we're used to seeing equations like this. I started with 5,000. And what happens every day after that? I increase by 25%. So the little thing to remember is I keep my 5,000 that I started with, and I add to it 25%. And I'm going to do that over and over again. I can use my model to determine how many cells there will be 1 week later. So in 7 days, if in 3 days I've almost doubled it, how many will I have in 7? So I'm going to do 1.25 to the power of 7. And 5,000. So I have a graphing calculator. So what I'm typing in is 5,000 times 1.25 little hat 7. Some of you have that y to the x button. Some of you have x to the y. There's variations for a power button, but we get 23,842 yeast cells a week later. Here's another problem that's similar. According to the U.S. Census Bureau's World Population Clock, the number of people in the world in 1950 was 2.5 billion. The population has grown at a rate of approximately 1.7% per year since then. Create an algebraic model to predict the population in 2020. So the amount of people, you could do P for population, whatever you like. Similar to the last one is we started with 2.5 billion. So we need to remember that A is in billions of people. So we started with 2.5, and what is our rate of growth? Well, I know I'm going to keep that 2.5 billion. I'm growing, so my B value or my base has to be bigger than 1. So I'm going to do 1 plus my percent growth as a decimal. So it's been growing at 1.7%. So I am going to write that as a decimal. Decimal 0, 1, that would be 1%. 1.7%, I just tack that 7 on the end. So my base or rate of growth is 1.017 to the n, where n is number of years. Since, just check that, 1950. Okay, so if I want to know how many people since 1950, and I'm looking at 2020, 1.07 to the 70 years. 2.5. So on my calculator, 2.5 times 1.07 to the power of 70. And want to venture a guess? Times 1.07 to the power of 70 equals 284.97 billion people. Frank knows that light intensity reduces by 2% for each meter below the water surface. His underwater camera requires a minimum of 60% of the light at the surface to operate without an additional light source. Is Frank able to take pictures at a depth of 23 meters without an additional light source? All right then. So we are decreasing in the amount of light. So that's going to change our equation a little bit. So I'm going to do A, where A is amount of light, in percent, because that's what I want to know. I want to know how much light and if I'm able to take pictures. So we start, we assume, with 100% of the available daylight at the surface. And as we go each meter below, we're going to lose 2%. So what is my base or my rate of growth if I'm losing 2%? So the temptation is to say it's like the other ones. We would have 1 plus 0.02. But I'm not increasing 2%, I'm losing 2%. So my rate of growth is going to be 1 subtract 0.02. Or you're keeping 98% of the light. I don't know if that explanation helps or hinders. Okay, so 1 subtract 0.02, and my x value would be the number of meters below the surface. I want to know what the percent is at 23 meters below. So we want to know if I'm okay, if I am at 60% or better. So let's see. 100 times 0.98 to the power of 23, which is 62.83. So I have almost 63% of the available light, and it says I'm okay if I have 60%. So he should be okay and doesn't need an additional light source. But he's gonna very soon. He does not need an additional light source. We will try a few in class.